Charges can be arranged in many different ways. And we're going to consider a fairly common arrangement of charges today. And it's charges that are arranged in such a way that they generate a uniform electric field. Or at least approximately generate a uniform electric field. So here's kind of an example of that. Suppose I have two plates. Much like I have right here. So I have here, I have two plates. They're just two cylindrical plates, and I can move them back and forth. Now, suppose for a minute that I connected these plates to a battery, and I connected the positive end to this plate, and the negative end to this plate. If I were to do that, we would build up charge on the plates. That's exactly what I'm drawing right here. I have two plates. One plate is positively charged, one plate is negatively charged. And we're going to suppose that the top plate gets a charge plus Q, and the bottom plate gets a charge minus Q. Now, this might not seem like a very useful situation, but it shows up in many different places, both in engineering and in biology as well. So for example, we could look at the charge buildup due to sodium and potassium pumps in a neuron. And if we look very close to the surface of a neuron, the neuron's going to appear flat, just like the Earth appears flat if you're living on it. And so we'll see the buildup of charge in roughly the shape of plates, at least over a small area. So neurons are one example where this shows up. Turns out these also show up in cathode ray tubes, which is what we used to use in old TV sets. So we want to be able to describe the electric field between these two plates, which we can do just by first remembering the rules for drawing electric field lines. Remember, we're going to consider some test charge here. It's always a positive test charge. And this test charge would be, if it's positively charged, would be repelled by the positives and attracted to the negatives. So it would feel a force down. And in fact, this arrangement of charge gives a uniform electric field, at least between the plates in the middle. It's uniform. By uniform, I just mean the electric field is constant. It points in the same direction, and it has the same magnitude everywhere inside the plates. Outside the plates, it's a little bit different because the electric field will leak out a little bit, similar to what we saw when we looked at dipoles. But inside the plates, we get a uniform electric field. Now, how big is that electric field? Well, there are different ways to find the electric field between the plates. We've talked before about how we can use superposition to compute the total electric field for a bunch of point charges. So I could do that for every proton and electron in the two plates. That would be very time consuming. We could also do it using calculus by integrating up a bunch of different tiny segments that all have a uniform charge. But we're going to do this a little bit differently. We're just going to write down the formula. And in this case, the electric field will have a magnitude. It's going to be dependent on the magnitude of the charge, divided by epsilon naught. Remember, epsilon naught is the permittivity of free space, divided by A, where A is the area. I'll remind you that epsilon naught is 8.854 times 10 to the minus 12 Coulomb squared per meter squared. What I have here is an old school oscilloscope, which is what you use to measure voltages in circuits and different electronic pieces of equipment. And the way it works is you plug in some voltage and it will fire an electron towards the screen over here. And you can see a little fluorescent dot right about there. And that fluorescent dot is where the electron is hitting. Basically, we're firing the electron towards the screen, and the screen will start to fluoresce. And what we can do, we can plug in a signal and use the dot to measure the electrical signal. But how that works, we're going to show in just a second. But I just want to show you that I can move this dot back and forth. And furthermore, I can move the dot up and down. So I can change where the electron is actually hitting the screen just by adjusting the controls on the dot. And it turns out that we can actually measure the electrical properties of a circuit by connecting the circuit to the oscilloscope and using the parallel plates that we showed before to adjust where the electron is going to hit the screen. Let's see exactly how that works. So how does my oscilloscope work? Well, inside my oscilloscope, we have something called a cathode ray tube. And the cathode ray tube is made of a few relatively simple pieces of electronics. First of all, we have an electron gun. It doesn't actually look like this, not actually a gun, but I'm going to draw it that way. Essentially what a cathode ray electron gun is going to do is it's going to spit out electrons in a beam towards the screen. Okay? Those electrons are then going to come through the cathode ray tube and hit my fluorescent screen, causing there to be a dot that lights up. Now, how can we control where that dot is going to go? Well, the electron beam comes out this way. By the way, by electron beam, I just mean a steady stream of electrons that are coming through. So there's a bunch of electrons in here, a bunch of negative charges that are coming through. And they have to pass through a set of parallel plates. And this set of parallel plates, we can connect to some part of our circuit. Maybe some part of our circuit is connected to a battery. So there's some voltage difference between those plates, which is going to cause the plates to gain a certain amount of charge. That charge will give the plates an electric field. There's going to be an electric field between the plates. And as the electron beam reaches the plates, originally it might have been going straight and making a dot right in the middle. But now, the electron is going to be deflected because there is electric field. So if my electric field is pointing down, which way is my electron beam going to be deflected? It turns out, if you recall that the positive charges have the electric field coming out of them, we know that the electron is going to be attracted to these positive charges, repelled by the negative charges. So it's actually going to move in the opposite direction of the electric field. It's going to get bent upward. And as it comes out, it will be deflected and fluoresce at the top of the screen. So what we can do with our oscilloscope is by connecting different bits of electronics, we can actually measure how much of a voltage difference there is in our battery or any other bit of electronics, because the voltage that we apply, we'll talk more about voltage later in the term, but the voltage we apply will be related and directly proportional to the electric field that we get. So it will be related to the amount that this beam is going to be deflected. So just by measuring how far up the dot goes on the screen, we can figure out how the electron beam, how strong the voltage is in our circuit. This is also going to be useful for generating, if you want to build an old school TV set, well, all you have to do is get some fluorescent screen and put different pixels on it. You can have the pixels be different colors. So usually what people choose is red, green, and blue. So we call these RGB. And by directly hitting each of the red, green, and blue pixels, you can make a color image on the screen, which is exactly how old school TVs and old school computer monitors used to work. Another common place to see uniform electric fields is in gel electrophoresis. So let's say you're a biochemist, you have DNA or some other molecule that's charged, and you want to separate it from other molecules in solution. Well, what you can do is you can run a gel. So the way this works is you set up some gel, usually agarose or some other mixture of materials. You have two electrodes, which you set up. One will be positive, one will be negative, the orientation of which will depend on whether you have a positively charged molecule or a negatively charged molecule. You deposit your chemical in some wells, and then you turn on your electric field. So what's going to happen is your molecule here is going to experience two different forces, one of which is some electrostatic force, which can be written, again, using our mantra. We've said that charges create fields, and then fields create the forces on other charges. So we can just write the force on that molecule as going to be as equal to the charge of the molecule times the electric field. There's also some sort of backwards frictional or drag force on the molecule, which will depend on how fast it's going, generally speaking. So that eventually these two forces start to cancel out. The molecule moves through at a certain rate. Now, that frictional force is going to depend on a few things, one of which is how fast the molecule is moving, another of which is how big the molecule is. So if you have a larger molecule, it's going to have a more difficult time making its way through the gel. That being the case, if you have a bunch of different molecules, you can separate them based on their size and based on the amount of charge they have to get a picture where you get certain molecules that make it travel a large distance through the gel. These are going to be the smaller molecules, the molecules that can make it easily and wiggle their way through the gel molecules, and also the molecules that are the most charged, that they feel the biggest force on them. So using electricity, electrostatics, and by generating uniform electric fields, we can do a bunch of different very important chemical separations, and we can begin to understand molecules and how they interact much more efficiently. The last thing that I will note is that if you have a uniform electric field and dipole molecules in that field, those molecules will experience a torque that wants to align them with the field. For example, suppose we have an electric field pointing up as drawn here, and we have some dipole molecule drawn in green with a positive end and a negative end. Well, that dipole molecule is going to experience a torque because the positive charge is going to feel a force up. Just draw the forces in here. The negative charge is going to feel a force down in that electric field. So there's going to be a counterclockwise torque on that molecule. And what you will find is that molecules will tend to align with the field. There's a similar principle that works for things like NMR, except it's a magnetic torque causing the magnetic moments of different atoms to align. But in general, when you have an electric or magnetic field, molecules inside that are dipoles are going to try to align themselves with the field.